Hello everyone, welcome to the 7th tutorial for the computational fluid dynamics using finite volume method. So today we will start by start an important topic which is called stability analysis. So in the previous tutorials and classes we have seen unsteady diffusion problem a parabolic which is the unsteady diffusion problem, which is sort of a parabolic problem, and we will see how to we will see for the different time stepping schemes that we have seen. For example, for we had taken something like the phi is a linear combination of the two time steps, that is at phi at 1 and phi and 0, and this is just what is called phi dt of t or t plus delta t, and this is modeled as a linear combination between two time steps, right? So here what we will do is that we will try to see how the different time stepping schemes that we have seen plays out, how stable they are and all the things. Okay, so let's begin by writing down the unsteady diffusion equation. So which is nothing but dou by dou t rho phi is dou by let's not use this dou term, the del dot gamma grad phi, right? And we will assume and also a source term sp. So we will assume 1D problem, and also the sp will be modeled as sc plus sp phi p, and what else, and a linear profile assumption, at the faces, the gradient of the faces. Okay, so from here it is quite straightforward, right? So here what we will do is that we will integrate both in space and time, right? So cv and t plus delta t, then dou by dou t rho phi dv and dt, right? And this one we if you remember, we had written it like this. Okay, so we just interchange these integrals. We do the interchanging of the integrals, and the dou by dou t term can be written as rho times, we will assume the rho is constant. Okay, it does not change with the with space or time. So we'll write phi p 1, which is at, so let's just write it down. Phi p 1 will be, it corresponds to phi at time t equal to t plus delta t. Let's not write time t equal to, like the time equal to t plus delta t, and phi naught will correspond to phi at time t. Okay, so we wrote it something like this: phi p naught by delta t, and the integration over the control volume is nothing but delta v, right? It will just get multiplied with delta v. Okay, so the left hand side is quite straightforward. So rho delta v in a 1D problem, it is nothing but delta x by delta t phi p1 minus phi p naught, right? So now we have the the right hand side is well populated. Now we will look at the left hand side is populated. Now let's look at the right hand side. Okay, so if you remember from all the other just a minute. Okay, so this is nothing but del dot gamma grad phi, which we apply the integration over time and space. Let's take the time at the outside, the integral, and cv dv dt. Then our familiar mode, we just do the Gauss divergence theorem and break the integral and split the integral into the summation of the different cell phase values, right? Let's write it down here. T plus delta t, and it's nothing but gamma d phi dx and a at different phases. This will be nothing but a summation and dt, right? And what did we say? That we can we can assume this integral to be a linear combination of the values here, where the value is nothing but this part, the linear combination of value at time step t and time step t plus delta t, right? So what it will be? It will be nothing but f of summation gamma d phi dx a at some phase. Okay, let's write that fc phase, and at time 1 plus 1 minus f summation gamma d phi dx a fc at time step 0, right? Similarly, we will do for the same thing for the integration of t plus delta t sc plus sp phi p delta v, which is in our case is nothing but delta x, is nothing but sc plus sp phi p at the time 1 times f plus 1 minus f sc plus sp phi p at time 0, right? Okay, so now that we have all our equations here, let's club them together and manipulate it to get our familiar AP phi p form. Okay, so now we have in the left hand side we have rho delta x by delta t times phi p1 minus phi p naught is equal to f. We'll just break it down, right? This will be nothing but the summation of the two phases. In the 1D case, it is the east phase and the west phase. East phase and the west phase. So let's write it for the east phase first. Okay, so the east phase, let's write it down. So it will be gamma, we'll assume the area to be unit area, so 1, we'll just ignore the a part here. So gamma by delta x, and we have phi east at time step 1 or phi p times step 1, right, and minus of gamma delta x phi p1 minus phi w1, right, and for the this case it will be same. Let me just copy it, it will save some time. Sorry. And we'll just replace the one superscript with 0. Okay, don't make mistake it with a power, so I'll just give a bracket here. Okay, now that this part is done, and we are only left with the source term, right? So the source term will be nothing but f times sc1 plus sp1 phi p1 plus 1 minus f sc naught plus sp naught phi p naught, right? Now we are done with discretization and we got the final equation. Now we'll just club them together in our familiar AP-Phi-P form, right? So in the left hand side we'll keep the unknown phi p1 which we are interested to find, that is the value at the next time step at the present cell, right? Okay, so what will be the coefficients? So first one will be this one, which is nothing but rho delta x by delta t, then this term is done. We have this term which will be plus, so it will be f times gamma by delta x. This is done. This will again be this is minus, it will go to the left hand side, it will again be plus, and also it is multiplied by f, so we will take it inside the bracket delta x plus, is there any term which is getting multiplied by, yeah, this term, right? So this will be okay, sorry, so there will be a delta x here because of the volume integral. Alright, so we have this term also, which is nothing but it will be minus, right? This will be minus f is outside, so minus sc delta x sp, sorry. Okay, so now this is done, and what have we now? Let's write p east of 1. P east of 1 will be nothing but f times gamma delta x. Phi west 1 will be similarly f times gamma delta x, which comes from here. What else? Nothing else, right? Now phi p naught. So what is phi p naught? Phi p naught will have this coefficient, this is negative, this will be plus, so rho delta x by delta t. Phi p naught, where else we have here? This one, right? So plus 1 minus f okay, let's not write here plus, because all these terms will of phi p naught will have minus signs, right? So we'll just take the minus here and just add these coefficients. So gamma by delta x plus gamma by delta x. What else is there? We have this term, right? So plus, oh, not plus, this will be minus, right? minus sp naught delta x. What else is there? Right, done. Okay, so now that these are done, what are we left with? We are left with phi e naught, phi w naught, and these source terms, right? Let's club them together. So plus phi east 1 minus f gamma by delta x plus phi west 1 minus f gamma by delta x. These two are done, left with this one only. So it will be delta x times f sc1 plus 1 minus f sc naught, right? So we have all our terms ready. Let's just name them so that it's quite easy for us to handle. This will be ap naught. We'll write it as a east, a west. Similarly, this is also a east and a west, and this is also ap naught, a east and a west, a east, a west, and so on, right? So let's write down the equation. So finally we are left with something like this. So we have phi p1 ap equal to phi east 1. So let's just write it as f times phi east 1 a east plus phi west 1 a west, right? This term and this term, and we'll write this as plus 1 minus f a east times phi east naught plus a west times phi west naught, right? This is gone, this is gone. What else is required? Plus a, will have phi p naught ap naught minus 1 minus f a east plus a west minus sp naught delta x. This is also done. Oh, sorry. And we'll just write it as b, which is nothing but this term, right? Okay, so now we have some interesting formulation. We can see that for the value of f, different values of f will get different schemes, right? So if the value of f is 1, we'll see that we'll see this term totally vanishes, right? This term and this term totally vanishes. So what are we left with? We will be left with phi p1 ap ae right plus ap naught. This term will also vanish, right? ap naught phi ap naught phi p naught plus b, right? And the b will be a little bit different, right? B prime, because this term will also vanish. It will only have SC, what it will have? It will have only SC1 times delta x. Okay. So now that we have this form, this is sort of called an implicit time stepping. So what does implicit time stepping mean? Here what are the unknowns? We have this as unknown, this as unknown, and this is unknown, right? Only this part is known, right? And also if SC varies with time, for example, if SC is a function of time, then this is also an known, for example, and if it is a function of phi p, then it is also an unknown, right? So we'll just ignore this part. So what do we see now? That we are left with a system of linear equations, right? We have a system of linear equation to solve. Right. So we see that in this form, when we have a value of f is equal to 1, we will have a system of linear equation to solve. And what is the AP here? If you look carefully, the AP, where have we defined? The AP in this case is nothing but AP naught plus the summation of the neighboring coefficients, right? So AP naught plus A east plus A west and the source term, right? We will just ignore it for now. So in the limit that the source term is 0, we will see that this kind of time stepping gives us a bounded solution, right? So what is a bounded solution means? So in zero source condition, we will see that we are left with nothing but AP phi p equal to A east P east and this is nothing but A P naught plus A west plus A east, right? So what does it tell us? That this thing that we have is sort of a bounded by its neighbors. So now rather than having two neighbors in the left and the right, we have another neighbor which is a neighbor in time, right? So if we see the cells like this at say time t is equal to t1, and this is the value of, so this is the point P, point west and point east. This is t is equal to t2. So we'll see that this point P will depend on its neighbor in space as well as the neighbor in time, right? So in this way we can say that the implicit time stepping scheme that we have written down here is sort of giving us a bounded solution, right? And also if you look at the AP naught term, so AP naught term, not AP naught term, the coefficient of the AP naught, Phi naught. If you look at this is a minus sign also, right? So this will this may make our coefficient. So for example, let's write this coefficient as AP star. So AP star might become 0, right? It might become 0 when AP naught is less than this whole value, and this will again cause the result in an unbounded solution, right? Why is that? I think sir has also explained it. For example, if you have some phi p which is having some related to phi p naught, and this is negative, some negative coefficient it is having. So if phi p naught is a very high value, in the next time step the phi p will be very low, right? Because this is having a subtractive effect on the phi p. So what will it cause? It will cause, like for example, if phi is growing like this, if it is growing, then it will decay, then it will again grow, and it will again decay like this. This will cause an oscillatory solution, and finally the solution will blow up. Yeah. Yes. Yes. So if you see here, this is so you have a domain, right? So you have a domain which has many cells. So there is a, say, phi p naught, phi west naught, phi east naught, and everything at time is equal to t1. Now you apply the time stepping scheme, some dt time you progress, and now again this is the domain, phi e1, phi p1, and phi w1, right? Now if you look at this equation is very similar to what we had before, right? So before we had like AP phi p is nothing but a summation of A and B and phi and B, right? So and AP was nothing but summation of A and B, right? So what does this actually mean? So we can write that phi p is nothing but summation of A and B, phi and B by summation of A and B, right? This is nothing but AP. So this tells us that the solution of phi p is bounded by its neighbor. What does the bounded by its neighbor means? It means that the solution that we obtain using this discretization will give us value which are bounded by the maximum and the minimum neighborhood phi values. For example, if you say that just a minute, yeah. So say if you have a 2D problem, right? So this is P, this is north, this is south, this is west, this is east. So you have at north, say you have 100 degrees Celsius, you have 200 degrees Celsius, here you have 300 degrees Celsius, and you have 400 degrees Celsius, right? So the value here will be somewhere between 100 and 400, right? It cannot be less than that, or it cannot be more than 400. It cannot be physically 500 degrees Celsius, and it cannot be physically be possible to have 50 degrees Celsius if there is no source and sink. If no source and sink, right? So if there is no source and sink, this will be bounded. So this is called the bounded part. So this will be bounded by the neighborhood values. Okay. Now in this case, if you see, if you compare the situation where we had for a elliptical problem where we have a steady state solution, A and B and phi and B. These are the neighboring values in space, but we have here an additional we have here an additional neighbor, right? This is a neighbor in time. Okay, you understand now? So this value will depend on this, will be dependent on the west cell, or dependent on the east cell, as well as the cell, as well as the previous time step cell value. Okay, so in this way we can say that the scheme that we have developed is sort of bounded by its neighbor. The neighbors being in the sense that the neighbors can be both in space as well as in time. Also, if you look at the general form that we had derived, the general time stepping steady unsteady diffusion equation that we had derived, there is always a scope for having other neighbors also, right? So we have this, we can have this and all other things, right? All combinations of things, right? So we can have neighbors, we can have something like this, and we can have a case where the P depends on all of these neighbors. Okay, so these are the different type of conditions that we will explore later. So this kind of so this dependency comes from the implicit time stepping. Okay, and this will come as a consequence of the explicit time stepping, TSL, right? And this whole thing, this orange thing, will come out as a consequence of the Crank-Nicholson scheme, right? So where we have the f value of half. Okay, is that clear to everyone? I think I have, yeah. Okay, thank you. Okay, so now that we have seen that the explicit scheme has some good properties, right? So we do not have a case where we can go unbounded, because when can we go unbounded? We can go unbounded if some of the coefficients, for example, if we have a coefficient the AE and AW, either of them goes to negative, then this will cause a problem. This will cause our problem to become unbounded. Okay, because then we won't have bounded, then we won't have a what is called linear combination of, we will have a linear combination, but since it is negative, then we can expect some unbounded values. That means if we have some value here 100, some value here 200, we can expect something like 70 here, which is not the case if we have a negative coefficient. I think sir have already touched upon the negative coefficient, the problem that we have with negative coefficients. Okay, so now that we have developed the intuition for the implicit scheme. Okay, let me just write down the other observations that we have made. Okay, so the other observation what we have made was okay, it was the same in zero source condition. What we will have, we have a bounded solution, right? All coefficients are positive. Okay, so there is something we can tell that it is something like it is unconditionally stable. Okay, but what is that will come later. I think if you have followed sir's lectures, then it's quite clear, but we will again do some problems which sir has not done in class to demonstrate it. Okay, Now coming, if f is the value of f is 0, if the value of f is 0, we are only left with these parts, right? So we will have AP1 PP1 AP to AE okay. And what will the AP naught here be? So the AP naught here will be, okay, sorry, this is not AP naught, this is AP star, right? Because AP naught is this part. Let me just rewrite it. This will be AP star, and here the AP star is nothing but AP naught. AP star, okay. Now what does AP have? So AP will have what all things? So AP will have this all things goes to 0, is nothing but rho del x del t, nothing but AP, right? Because f is 0, right? So this whole term goes to 0. So AP is nothing but AP naught. AE and AW is quite straightforward, it is nothing but gamma by delta x. And what about AP star? AP star will have some trouble in this part. AP star minus, so 1 minus f, this will become f is 0, this is 1. A east plus A west minus SP naught. Okay. Now to have a bounded solution, we need to have all positive coefficients, right? So to make the equation positive, we will have AP naught should be always greater than or equal to A east plus A west minus SP naught delta x, right? So let's see in the limit of 0 source, what do we have? We assume there is no source. So what is AP naught? AP naught was nothing but rho times delta x by delta t greater than equal to 2 times of gamma by delta x, right? Now if we see this condition, we will have something like, so delta t should be always less than and equal to rho times delta x square by 2 gamma. Okay, so this is a condition that we arrive at on the basis of the non negativity of coefficients. Okay, we will reach the same conclusion using the von Neumann stability analysis that we will do. I'll touch upon later. Okay, but we see here that in the implicit time stepping scheme we do not have any such conditions on delta t, because all our coefficients here, all our coefficients of AP, AE and all those things, AP star also, are all positive, so we do not have any issue with that. Now what about if f is f equal to half? What then? If f is equal to half, let me just copy this whole thing. make life simpler. And let me just write AP naught plus F A east plus A west minus SP delta X. It's correct. Plus, yeah. Okay. Now let's put it this way. The new AP will be the F is just half. So let's just write 1/2. Here also 1/2. Okay, we have to write B also here, right? Because B is also having some F terms. Here B is delta X half of, okay. So B is nothing but delta X by 2 SC naught plus SC1. So it's just a simple average of the two time steps, right? So now if we see here, all these terms, these coefficients A, W, A, E, these are all positive, but something might cause an issue here, right? Because we have a negative sign here. Let's see how we can check whether this will give us a bounded solution or not. Okay, so this AP star, where AP star is nothing but AP naught minus half of A east plus A west. So in the limit of no source, in case of source equal to 0, this should be always greater than or equal to 0, right? To satisfy the non-negativity of the coefficients. Okay, so let's see. So AP naught should be always greater than equal to half of AE plus AW, right? So let's write it down. So half of AE is nothing but gamma by delta X. So 2 gamma by delta X should be less than equal to rho delta X by delta T. Again taking the T in the left hand side, delta T. So delta T should be less than equal to rho delta X square by gamma. Okay, this is for the case of Crank-Nicholson, right? Crank-Nicholson time stepping. Now in the, what did we see in the in case of the explicit scheme. So in the explicit scheme, we had delta t should be less than equal to rho delta x square by 2 gamma, right? Here we had derived this. So now we see that the explicit scheme is much more stringent delta t bound, right? More for delta t, right? Because if, for example, rho delta x square by gamma, the value, say, assume it to be, say, 0.1. So for an explicit scheme, we should have delta t less than 0.05, right? Because this is divided by 2. And for a Crank-Nicolson scheme, we will have delta t less than equal to 0.1. So in case of a Crank-Nicolson scheme, we can expect a bounded solution even when sorry for that. Yeah, so we can see that for the Crank-Nicolson scheme, we have a much more looser bound in case of delta t. So we can take a higher value of delta t by maintaining the boundedness of the solution. But why does this matter actually? So this matters because the more delta t you will take. So in a practical simulation setup, for example, you want to do the simulation of a turbulent jet which is issued from here from a nozzle, and you want to progress it to, say, 1 second, right? So if you take, say, delta t is more, then the computational time will be less, right? So if you take delta t value of 0.1, you can finish it in 10 time steps. But if delta t value is 0.05, you have to finish it at 20 time steps, right? So it will result in a double the time of simulation that we need. So this is a very at each time step it will take around some microsecond or millisecond. But if you see the big picture, we generally solve for a very high dimensional problems like 1 million, 2 million, 3 million grid points. If we take a problem of such scale, these kind of problem generally run for, say, 1 month or 1 week. So if we have a looser bound on the delta t, we can finish solving the problem in a lesser time. I will not say that we will be able to solve it in half of the time that we take in explicit time step, but we will have considerably less computational effort, because in the case of a Crank-Nicolson scheme, if you see that we will have both means we will have these unknowns, right? These are all unknowns, and on the other hand these will be known values. So we will again end up with a system of linear equations which we have to then implement either line by line TDMA or Gauss-Seidel or Jacobi. This will again take some extra computational effort, but what I wanted to convey is that the different time stepping schemes that we have seen here will allow us to choose the appropriate time step dependent on the problem. And also another important aspect of the different time stepping scheme is that for example, if you remember, for say for a linear linear interpolation that we have done, for example, for the gradient operator d by dx at some phase f, we will say, for example, we will take the phase east. It was nothing but phi east minus phi p divided by delta x, right? We had taken the linear profile assumption. If you remember, this is p, this is e, and we assume that the value of phi p is varying linearly from point p to point e, and it's very easy to get the gradient at the face, right? Now, if we this sort of gave us a second order accurate scheme, right? If you remember. For example, if we east, we expand, we do the Taylor series expansion about phi p plus dou phi dou x at p by delta x plus dou phi dou square p dou x square p delta x square by 2 plus order of delta x cube. I'm sorry, this won't be the case. Yes, so we say, for example, let me just show you the order of accuracy, then in the spatial context, then we will go to the order of accuracy in the temporal context. So we want the derivative here, right? So we want d phi dx at e. So we will expand the we will do a Taylor series expansion about the point phi e. So let's write it down. So phi p will be what? It will be phi east minus dou phi dou x. Say, let's just assume this is delta x and this also to be delta x. Just assuming, okay? And this will make our life easier. So delta x plus this, because we are going backward, right? So the p east phi p is in the backward direction from the east face. Then dou square phi, it won't be partial, it will be ordinary differential because it's only one independent variable at east delta x square by 2 plus order of delta x cube, okay? And phi east will be what? It will be phi small e plus d phi dx at e delta x plus alright. Now we will just say this is equation 1, equation 2. So yeah, please. Yes, yes, because we are interested in this derivative, right? Wherever we want the derivative, we will expand the, we will do the Taylor series expansion about that point. Because here you see the delta x is in the negative direction. So if this is the x direction, we will have to go backward, right? So that is why this will become negative. This is also negative delta x square, but since it's negative delta x squared, this becomes a positive quantity. Okay. So let's yeah. Which one? This one? Yes. Yes. But when we go to the cell center capital E, so from small e to capital E we have to move forward in the x direction, right? That is why it is positive. Since we have to move backwards, it is negative for phi p. Okay, so let's just okay. So what we will do is that we'll subtract phi equation 1 from equation 2. So what are we left with? We will be having then phi east minus phi p. These two terms will get cancelled. This will get added up, right? So this will become 2 delta x d phi dx at E. Then these two terms will also get cancelled, right? And we will only left with order of delta x cube. Now we just divide everything by 2 delta x. So we have phi E minus phi p by 2 delta x equal to d phi dx plus E plus some delta x cube divided by delta x. So it is nothing but this one, right? So we can write finally the d phi dx at face E is phi capital E minus phi capital P by 2 delta x plus some delta x squared term, right? And if you remember, this is nothing but the truncation error. Okay, this is nothing but the truncation error. So now that we have seen that the spatial derivatives are of some sort of accuracy is there, right? So there will be some errors. This is just an approximation. We will not get the actual value from this approximation. This will incur some errors, but we have to account for these errors so that we can construct. We have to account for these errors to assess the accuracy of the solution. Okay, so for example we have the delta x value of 0.001, right? So delta x square will be of something like 1 e minus 6, right? So like 0.00001, something like that, right? In the order of some 10 to the power minus 6, like. So if we are happy with this kind of errors, like for example we are computing temperature which is of the range of 100 to 500, and we are taking a delta x of this is how much, 1 millimeter, right? 1 millimeter, and we are incurring some error due to the spatial discretization which are of the order of 10 to the power minus 6. Okay, so this is very small when compared to 100 or 500, right? So this kind of judgment we have to make when we are constructing our problem or formulating our problem for any CFD calculations. So this kind of error estimations is very important both for the temporal discretization and the spatial discretization. So now that we have seen what the order of accuracy is for a spatial discretization, let us now go back to the unsteady problem and see how good is our spatial temporal integration assumption that we have, right? So for the source term, we will take the source term for convenience. So for the source term, say S, what did we assume? We assumed that we will take some t plus delta t, dt will take some, this is called a some averaged values, right? Some average value we take, for example from time t to t plus delta t, we assume that this whole time period between t and delta t is populated by some value s bar, rather than, for example, if say at t and t plus delta t, the source term varies like this. Okay, for example, like this it varies, but what will we take? We will take an average value of that. That average value can be the at s at t plus delta t. The average value can be at s t, and also somewhere between these two, right? So now let's see how what is the temporal accuracy of such approximations. Just 1 minute, please. Yeah, okay. So we will assume some value s bar is nothing but from t naught to t1 of s dt by delta t, where delta t is nothing but t1 minus t naught. Okay. So now let's assume some value of s at time t. Okay, some arbitrary s value at some arbitrary time t, and we will expand this s term about t1 and t2 and s1 and s t0 and t1, that is s0 and s1. So let's do this about, so Taylor series expansion about s1. Now Taylor series expansion about s2. Okay, sorry, no s2, right? Only s0. Let's write it in the bottom part. So here we are not concerned about whether this is positive or negative, this t minus t1, t minus t0. We are just don't bother about it, right? If it is negative, then it will be this will become negative, and if it's positive, it's positive. Okay, this is just some arbitrary time t. Now if we what we will do is that now we will integrate we will integrate this from T0 to T1. So if we integrate this from T0 to T1, so let this be equation A, equation B. Now for the S0 part, this will be again T0 to T1. And so this is negative minus dt and so on, right? So now these values S1 and all these things, we actually know this, right? We know this, and from these values we want to compute an average value, right? And we want to see that the technique that we are using to get the average term, how accurate is it, right? So now if we just we can just easily take these things out of the integral. Okay, and what about this part? This will be, so for example, if we take t minus say if we take p minus t1 is nothing but p, and the integration is for t0 to t1, we will have to change the integration also, right? So so at t is equal to t0, the p will become what? P will become t0 minus t1, which is nothing but minus delta t, right? T1 minus t0 is delta t, so t0 minus t1 will be minus delta t, right? And what about the upper limit? So at t is equal to t1, t1 minus t1 is equal to 0, right? Is equal to p. So our integration, this integral will change from t0 to t1 to minus delta t to 0. Same thing will be happening here also, but here the thing will be, we'll assume t minus t0 equal to p, and at t is equal to 0, t is equal to t0, our p will become 0, and t is equal to t1, our p will become delta t. So this will become 0 to delta t, right? And what will be the integral be? So the integral is p times dp, it will nothing but p square by 2, right? Simple integration. Okay, let's now get back. So our A equation will be t0 plus t1 s dt equal to s1, and dt integration t1 to t0 will be nothing but delta t plus ds dt at 1 and this will be p square by 2, that is nothing but t minus t1 whole square by 2. Okay, let me just write in terms of p, it will be easier. P square by 2, integration limits are minus delta t to 0 plus order of del t square, right, if you remember. And similarly for B we have S naught delta t and ds dt at 0, it will be also p square by 2, but the limits will be 0 to delta t, right, and order of delta t square. Now if we do that, the equation A will turn out to be something like this: t naught to t1 s dt equal to s1 delta t plus this will be 0 minus delta t square, this will be plus delta t square. So it will be, this will not be plus anymore, this will be minus ds dt at 1 delta t squared. Right, delta t squared, and what else, plus order of delta t square. Similarly for equation number B, we have t naught to t1 s dt s naught dt, sorry, delta t delta t, this will be plus, right, because this is delta t square minus 0. Okay, there is a 2 also here. Okay, and ds dt 1 delta t square by 2. Okay, so we have these values, right. Now let's just again check what was the s bar value that we had defined as. It's nothing but the left hand side that we have divided by delta t. So let's do that. We'll divide everything by delta t. So we have t naught t1 s dt divided by delta t is nothing but s1 minus ds by dt at 1 times delta t by 2 plus order of delta t square. Similarly here also, so t naught to t1 s dt by delta t oh yes, absolutely right, thanks for pointing it. Equal to s naught plus ds dt at, okay, this will be 0, delta t by 2 plus order of delta t. Okay, so this is nothing but the s bar, right. So s bar is nothing but s1 minus, or let's just write plus order of delta t, and here it will be s bar is equal to s naught plus order of delta t, right. So what does this remind you of? So if you remember, we assumed s bar to be something like f s1 plus 1 minus f s2 sorry, s naught, right. So now you can get idea of what is the accuracy of an explicit scheme and an implicit scheme, right. So if we take, say, f equal to 1, we have an implicit scheme, right. So only what do we have? So s bar is equal to s1, and it is very similar to this part, right, but this has an error of the order delta t. So we can say that the implicit scheme is first order accurate, right? So we can say that the explicit time stepping scheme, implicit time stepping scheme is first order accurate. But what happens if we put f is equal to 0? So if we put f is equal to 0, we have an explicit scheme. We have an explicit scheme. So what is that explicit scheme? It means that S bar is nothing but S naught, which is this part, right? But it has associated with it an error of order delta t. So what do we conclude from this part? We can see that both. Yeah, please tell. No. Okay. So if you see this, we are interested in this S dt t plus delta t, right? And we modeled it using some kind of f times s1 plus 1 minus f times s naught, right? So this is for the temporal integration. This is not in case of space. So forget about the yeah. Yes. This space discretization, this comes from the spatial discretization, right? This comes from the integral of cv del dot gamma grad phi dv, right? This part means the derivative is a spatial derivative, right? And it comes from the spatial integration, the volume integration that we have done. But in this case we are not doing the spatial discretization, right? We are just interested with the s dt, right? The temporal integration. Okay, right, absolutely. So both the explicit and implicit schemes are first order accurate, right? So what does this mean? It means that there will be, because we discretize our domain in both space and as well as time, right? You can what how to explain? So you can, so for example, let's take this 1D domain, right? Anand? Yeah. So we have a continuous field. We discretize it in space. We get like this a domain, a discretized domain, right? This will incur some error of some, say, delta x to the power n order, right? Then now when we have a parabolic equation, that is a temporally or marching problem that we have, we will discretize it in both space and time as well, right? So for example, say this is delta x and this one will be delta t. So this the time stepping that we are doing, we are discretize it in time as well. So this will incur some order of errors, say t to the power m, delta t to the power m. So previously we only focused in the elliptical problems, we only focused on the temporal discretization, but now since we have moved on to parabolic problems, parabolic PDEs now, and we have time dependent problems, then we now that we have arrived there, we are now more concentrated about the temporal discretization that we do, and what this kind of discretization, what will be the nature of the errors that are incurred because of this temporal discretization. Okay. Yes, absolutely. Absolutely. So the for the second order accuracy, accurate in time. Yes, absolutely. You have to mention that. So this comes from the uh, temporal discretization. Okay, and the spatial, sorry, and the spatial accuracy is second order in space. This comes from where? This comes from the linear profile assumption. Okay, so these are the two different concepts. Try not to club them together, but this is these are the two different errors that we incur because of spatial discretization as well as the temporal discretization. Okay, another, so there is a method called the spectral method. So by spectral method, it means that we do not solve it in a Cartesian domain, rather than we decompose the governing equations into different waves in the Fourier basis. Okay, so when we solve in the spectral domain, we do not incur any spatial errors, so the spatial errors goes to zero. But in time, when we are marching in time, some kind of error occurs because of the different time stepping schemes. Okay, now one thing to look at, so both the explicit, so another thing that we have observed is that both the explicit and implicit schemes are first order accurate, but the implicit schemes, not schemes, implicit scheme gives bounded solutions, right, and no restrictions in delta t, and explicit scheme may give unbounded solution, and there is a restriction on delta t's choice, right? So if you remember, where was we? For explicit scheme, what did we have? So we had that delta t should be less than equal to rho delta x square by 2 gamma, right? And this kind of restrictions we have for explicit scheme, but we do not have for implicit schemes, right? But another difference, but both of them are first order accurate. Okay, so now you have different characteristics of the schemes, right? Some will give you bounded solution, some may give you unbounded solution, some will have a restriction of delta t, other might not have one, and there is another aspect, another characteristics of the scheme, which is nothing but the order of accuracy. Okay, now if you see, the restriction is very tight, right? For example, if we try to, if for example, if rho and gamma are constant, and we vary delta x, right? So we want to, so for example, we did one simulation with 4 cells, or 5 cells. Now we want to do a simulation with 8 cells or 10 cells, right? So delta x will become, the new delta x will become delta x by 2, right? Delta x new will become delta x by 2. So if rho and gamma are constant, if delta x is reduced by 2, then delta t will have to be reduced by 4, right? Because delta t is scaling as delta x squared. So if we reduce delta x by some value, delta t will have to be reduced more, right? So you get the other characteristics that we have extracted from this limit, right? Now let's see about the Crank-Nicholson case, right? So what do we have for Crank-Nicholson? So let me just copy this part. Okay, so what does this say? This says that S bar is nothing but S1 minus ds okay, I don't think we will be able to extract the Crank-Nicholson case from here. Okay, so S bar is nothing but S1 minus ds dt at 1 dt by 2 plus order of delta t, and here we have S bar equal to S naught plus ds dt at 0 delta t by 2 plus order of delta t. So if we just add these two things, 2 S bar S1 plus S naught minus ds dt delta t by 2 plus ds dt delta t by 2 this is order of delta t only. Okay, I'm really sorry, I don't think we'll be able to extract anything from this part. We'll have to again do a similar kind of analysis. So let's okay, so do you want, so anyone, Anand or someone may tell, so should I continue with deriving the order of accuracy for Crank-Nicholson, because Crank-Nicholson will give you a second order accurate scheme, right? The accuracy will be delta t squared. I can derive that, and but it will be a bit lengthy. Or do you want me to go ahead and touch upon the von Neumann stability analysis? Okay, then I'll do it. Okay, I I'll just introduce you the method, and I think from that it will be very straightforward. Okay. Okay. So for crank Nicholson, what we will do is that so we will expand S1 in terms of at S, right? So S1 plus S plus, which will be ds dt t1 minus t. Let me just check. Yes, this is okay. Plus d square s dt square t1 minus t whole square by 2 plus order of delta t cube, and similarly s naught s plus ds dt t naught minus t okay. Now again we will do the integration. Let this be a, let this be b. Integration s1 will come out, sorry, similarly you will do for s naught. Okay, so t naught t1 dt t naught t1 s dt plus the same things. Just a minute. Now what is this? This a will become something like this, right? So s1 delta t, t1 minus t naught is delta t, and t naught by t t1 s dt. Similarly for b part, for equation b, it will be s2 delta t, this will be t naught to t1 s dt plus all the other terms. Then you will do a similar thing, you will just divide it by delta t. Okay, so what will you do is that you will again do the same kind of integration for both these terms, and you will divide it by delta t. Okay, then you will find that one of the terms get cancelled, one of the terms with plus minus what will you find is that the higher order term will get cancelled. If you just add these two things, you will get that the higher order term will get cancelled, and you will get something like this. You will get something like this finally. T naught to T1 by delta T is nothing but half of S1 plus half of S2 plus order of delta T square. So finally you will have something like this. Okay, so I will not go through the entire process of how you will do that, because anyway I think this is in your assignment. Okay, you understand how to go about this problem? Yes, yes, sure, sure. Okay, it's only 25 more minutes. So what I will do is that I will briefly touch upon the Born-Neumann stability analysis. Okay, so initially we saw that the for the implicit and explicit scheme, to assess whether the solution is bounded or not, we imposed the non-negativity of the coefficients, and we got some values. We will get the same thing if we do for the von Neumann stability analysis. So von Neumann. So in the lectures, sir have done for the explicit scheme, and if you have followed the lectures, sir also showed that this kind of a condition we will reach at something like this, but now we will do it for a explicit scheme, right? So we will do the same thing for the explicit scheme, sorry, implicit scheme, and we'll show that this kind of scheme is stable no matter what. Okay, let me just, no matter what time step you choose, but does not necessarily means that the solution is correct or accurate. Okay. Okay. We have to take some assumptions, right? So source is 0 and constant coefficients. So these are some of the assumptions that we have to make for doing a von Neumann stability analysis. So what did we have? We had AP is nothing but AP naught plus A east plus A west, right? Let me just check it once again. So implicit scheme, yeah, AP naught plus AE plus AW, and AP star is nothing but AP naught. AP naught is nothing but rho delta x by delta t. AE, A west is nothing but gamma by delta x, and AP star is nothing but AP naught. Okay, so now what did sir say? Sir say that we will assume. So what does the stability analysis actually tell you? It tells you that we have to bound around the errors. Progressing through time, right? So there is, I hope everyone is familiar with the concept of round of errors. So if you see, the numbers will have some say some So 10.1256793 something like this. This is the actual number in real life, but what happens in a computer is that there is something called floating point numbers for FP16, FP32, FP64, double float, this kind of different data structures, not data structures, different kind of um, variables are there which are able to store different values, right? So for example, if you have a in a computer which has a which cannot store a lot of digits, it will only truncate this number up to say this, right? And this is something called the round of error, right? So these kind of errors are generally very predominant in computational scenarios, and these kind of errors might grow, right? Because something called 10.12567 is not same as, is not equal to 10.1256793 right? This is not the same thing. So this inability of a computing system to store our required numbers to infinite precision generally incurs a round of errors, and this round of errors we have to bound this round of errors by method of constructing some improved schemes or some best practices which we need to follow, so that this kind of errors does not grow as we go ahead in time, right? So if we compute some phi p with these round of errors, this phi p will be again used to compute phi p1, which will have some more errors. This will again will be compute to phi p2. This will again pass down the error, right? So since the error is being passed down from one time step to another, it is very important to get the to see whether the error is growing or not with every time step, right? So there is a metric called the amplification factor, which should be less than or equal to 1. That means the error at a time t is equal to t plus delta t divided by error at time t should be always bounded by 1. Okay. So now let us assume some kind of imaginary computer which is able to store all these values at infinite precision, which is denoted as capital phi. So capital phi p a p equal to a e capital phi e plus a w capital phi w plus a p star capital phi p naught, right? This is 1 1 1. Okay. Now we subtract these two equations, right? If we subtract these two equations, we will be only left with the errors. So it will be, let's define it like this: phi p minus phi is nothing but the error. Okay. So we have error p, a p is nothing but error east, a east plus error west, a west plus error p naught, a p star. Okay. Now comes the next step. We have to model the error. What will we use? We will use the Fourier basis. That means we will assume that the error, which may be something like this, and we will break it down into different Fourier modes, right? This is nothing but a linear combination of different sine waves and cos waves depending on the different amplitude and the frequency, right? So this is nothing but the amplitude lambda m and frequency, that is the km. Okay, we'll just model it. Okay, so let's model it. We'll model epsilon as a summation of m e to the power minus I k m x e to the power lambda m t. Okay, yes, yes, please tell. Tell. Can you tell me? Can you say again? Okay, so exponent, you know, right? So exponent e to the power I theta is nothing but sine cos theta plus I sin theta, right? You know about this, how to expand this exponent for? This is this. Okay, so this acts as the amplitude. Okay, absolutely, you can take anything. So generally the exponential, we generally tend to model our even if it is not I, there is not I, we can again what is called split the exponent e to the power lambda mt into cos theta and sin theta, cos lambda and sin lambda, right? So because of that, due to the universal nature, so these are nothing but the Fourier basis. Okay, so if you just have a take a glance at the Fourier expansion that you have been taught in engineering mathematics, then it will be, I think, more clear. So this is sort of a amplitude part, and this is the how the different waves at different wave numbers are behaving. Okay, this is the amplitude part and this is the frequency part, right? This km will dictate how fast the wave is moving, and the lambda will dictate how large the amplitude will be. Okay, okay, so rather than looking at all the modes, we will just concentrate ourselves to only one mode, right? Only one mode of I'm sorry, just give me 1 minute. Yes. Yeah, so we model the error in terms of as a linear combination of different not linear combination, just a summation of different modes, but we will only concentrate upon say only one mode and see whether it's stable or not. So we'll just model it using something like this I k. We'll just remove the m part because we are only dealing with one e to the power lambda t. Okay, so now each of the errors we can just replace it using this formulation, right? So ep1 will be nothing but e to the power I k x times e to the power lambda t plus delta t, right? Because this is in the next time step. Epsilon 1 is at time step t plus delta t. Similarly, epsilon east 1 will be e to the power I k east is nothing but x plus delta x e to the power lambda t plus delta t. Similarly, west, it will be e to the power I k x minus delta x and e to the power lambda t plus delta t. And finally this part, so EP naught will be nothing but e to the power I k x times e to the power lambda t only, right, because it's at time step t is equal to 0. Now let's assemble all these things together. So AP e to the power I k x e to the power lambda t plus delta t, A east to the power I k x plus delta x e to the power lambda t plus delta t. This will be minus delta x e to the power lambda t plus delta t plus e to the power I k x e to the power lambda t and AP star. Okay. Now we will divide everything by e to the power I k x by and e to the power lambda t. Okay. So what do we have if we divide that? We will have AP times, this will get cancelled, e to the power lambda delta t is equal to AE e to the power I k delta x e to the power lambda delta t plus AW e to the power minus I k delta x e to the power lambda delta t plus AP star, right? Now the amplification factor that we had, what is that actually? So amplification factor is nothing but epsilon 1 will be epsilon naught. Okay, it is nothing but e to the power I k x e to the power lambda t plus delta t divided by e to the power I k x e to the power lambda t, which is nothing but e to the power lambda delta t. Okay, we will write it as g. So what do we have here? So we are left with e to the power AP g AE g e to the power I k delta x plus AW g e to the power I k minus I k delta x plus AP star. Now we'll take everything to the left hand side and take g, and we are finally left with AP naught divided by AP plus AE e to the power I k delta x plus AW e to the power minus I k delta x. Okay, this is what we are left with. Yes, right. Right. Thanks for pointing out. Now what about the e to the power I k delta x? It will be nothing but, so let's just write it. So AE and AW are the same thing, right? So we'll just, and AP is nothing but AP naught plus AE plus AW, right? We'll just keep it that way, and let's just concentrate in this part. So minus, we'll just take minus gamma by delta x, which is nothing but AE and AW. This will be cos k delta x plus I sin k delta x plus cos k delta x minus I sin k delta x, right? These two will get cancelled. So finally we are left with AP naught AP minus gamma by delta x times 2 cos k delta x. Alright, now what do we have for a stable scheme? We have to see that the modulus of the amplification factor should be less than equal to 1. Okay. So what does this tell us? It tells us that minus 1 greater than equal to AP naught by AP naught plus 2 gamma by delta x minus 2 gamma by delta x cos k delta x. Okay, this part is clear. I just expanded the AP naught or AP term, right? I just expanded the AP term to get this. G is less than or equal to 1, but there is a modulus, right? So if there is a modulus, so even if minus, if the G is negative, say if the G is less than 0, if G is less than 0, then what it will be? Then mod G will be always greater than 0, right? So to take this, take the two conditions where G can be either negative or either positive. So if G is positive, so if G is greater than 0, we will only have this condition, right? G less than or equal to 1. But if G is less than 0, okay, so if G is less than 0, we will have this condition, right? So it should be greater than or equal to minus 1, right? It should be greater than or equal to minus 1, because if it is greater than, if it is less than minus 1, for example it is minus 2, the modulus of 2 is 2, which does not satisfy this inequality. Okay, I just skipped one step. So yeah, so if there is if ever if you are faced with this kind of problems which have a modulus operator, then you will have to take the both the conditions, whether when the variable inside the modulus can be either positive or either negative. Okay. Okay, so now what is this? This is AP naught. I'll just make it a little bit more simpler. AP naught plus 2 gamma by delta x 1 minus cos k delta x. Okay. Okay, this part is fine. So now again we will again have to do some manipulation here. Here 1 is nothing but sine square k x delta x by 2 plus cos square k delta x by 2. I am just, this sine square a plus cos square is equal to 1. I am just expanding this 1, and cos k delta x we can assume it to be of the form cos 2 k delta x by 2. Okay, so we will expand it using the trigonometric relation of cos 2 theta. So it will be nothing but cos k delta x by 2 plus sine k delta x by 2. This will be squared. Okay, now we'll just cut all these two things. This will be added, this will become, so AP naught nothing but AP naught plus 2 gamma delta x times, this will become 4, right? 2 will be getting multiplied here, 2 gamma by delta x sine square k delta x by 2. okay, and minus 1. Okay. Now the fun part. This, let's look at this inequality. Okay, for sine square k delta x by 2, the sine theta may have a negative value. It varies from, so sine theta will have a values from -1 to 1, but sine square theta will only have value from 0 to 1, right? Because it's just square. So the maximum value is positive, always positive. So sine square theta is always positive, and the maximum value is 1, minimum value is 0. So we are not. We will see whether when sine square theta is, when sine square k delta x by 2 is 0, this is nothing but AP by AP is 1. So this equality is satisfied. So when it is the maximum value of 1, then what is the denominator? So denominator will be having AP naught by AP naught plus 2 gamma by delta x, and we all know that this is always positive because delta x is positive, gamma is positive, and 2 is positive. AP naught is also positive because AP naught is nothing but rho times delta x by delta t. All of these terms are positive. Okay, so when a positive and positive gets added, so this denominator will be always greater than the numerator, right? So this, the inequality condition is also satisfied here. Okay, so this right hand side inequality we are done with. It is always satisfied, right? Everyone okay with that? Okay, let me just write it down nicely. AP naught 2 delta x sine square k delta x by 2 are always positive. Okay, so what does this mean? So at minimum sine square k delta x by 2 value, that is 0, we have AP naught by AP naught is equal to 1. So this satisfies the equality at max sine square theta value, that is 1. It will be nothing but AP naught by AP naught plus 2 gamma by delta x. Since this is also positive, so denominator is always greater than numerator, right? So since the denominator is always greater than numerator, the inequality is also satisfied. And now looking at this part, this we do not have to do anything, right? This is very straightforward because this part is always positive, right? So AP naught is positive, 2 gamma by delta x is positive, sine square x square is positive, and there is no subtraction sign, right? So everything is positive. So this whole thing will always be positive. So what do we have? We have that the condition is always true that the amplification factor is less than or equal to 1. So what do we finally observe? So we see implicit scheme for diffusion equation is always or unconditionally stable. Okay. Okay, so I think that's enough for today. Any questions from this von Neumann stability analysis? Yes, this part, right? No, this is also defined. No, I told you that the whole thing. So if you see, uh, if you have this part is positive, this is positive, this is positive, this is also positive, right? All the terms are positive here, and there is no minus sign. We are only adding things. So if we have all the things that are positive and we are not subtracting anything, then this whole thing will only be positive only. No, it has no way to become negative. No, not at all. So since this term is always positive, since this term is always positive, this inequality is always satisfied. Okay, so this is for sine theta. Okay, so this is sine theta, but we have sine square theta. So sine square theta can never be negative, right? So this is the condition that the left hand side inequality is always satisfied, and for the right hand side we have shown that here. So we see that there is no limiting condition. We can take any delta t for a stable bounded solution in case of a unsteady diffusion equation using the implicit schemes. Okay, so that was the main. So what will be the takeaway from this previous week 6 or week 7? Scheme as well as the explicit scheme, but there is no bound for the delta t for a stable solution in case of the implicit scheme. Okay, so we took two routes to arrive at the same conclusion, right? So first we saw we were imposing the non-negativity of the coefficients, and we got a bound for delta t. Then we applied a little bit more complicated approach, the von Neumann stability analysis, and from that also we got the same results. Okay. Okay, so today we'll stop the tutorial here, and okay, so Deepraj, I'll suggest you a book. Just a minute. Okay, I think the full book is here. You can just visit this link and download this book. This is a quite good book for getting started, because and it is not very thick book. You will be able to follow it very nicely, very simple mathematics, and same kind of notations that sir is using in the course. Okay, I hope this helps you. Thank you very much. Okay, so I'll end this tutorial. I hope all the doubts are clear, and I will meet you in the next class. Thank you, Reshma. Okay, bye everyone.